There's a second interesting place where ellipses pop up, and that's in the context of orbits, so objects moving around in space under the influence only of gravity. So Kepler noticed that if you imagine that the sun is at the center of the solar system, then all of the planets move around orbits that are actually ellipses. And it turns out that the sun is at one focus of the ellipse. Isaac Newton actually figured out the mathematics of why this is the case. It turns out that it's because the force due to gravity of the orbiting object is proportional to the reciprocal of the square of the distance between the two objects. So it turns out that that's enough to make this happen. So in general, when you have some very massive object and some less massive object that's orbiting, then the smaller object will move in an ellipse around the larger object, and the larger object is at a focus of one of the ellipses, or one of the foci of the ellipse. The other focus is just sort of hanging out in space somewhere. It turns out that actually the two objects don't have to have hugely different masses. They could have similar masses, but in that case, one of them doesn't stay in the same place. They both sort of orbit each other around a common center called a barycenter. But anyway, the idea here is if you have something small orbiting something big, then on an orbit that comes back and repeats, then that orbit is an ellipse with the large object at one focus. So let's see how we can use this idea. So let's look at the orbit of Earth. So the orbit's aphelion, which is the furthest distance that it ever gets from the sun, is 1.52 times 10 to the 8th kilometers, so a pretty good distance there. And its perihelion, that's the closest distance from the Earth to the sun, is 1.47 times 10 to the 8th kilometers. So let's figure out what is the semi-major axis and the eccentricity of the Earth's orbit. So when describing orbits, astronomers usually use these two parameters, so semi-major axis and eccentricity, for various physics reasons. So let's figure those out. Let's try to draw a diagram of this situation first. So we have the sun in the center of Earth's orbit, well, really at a focus of the Earth's orbit. And let's see, the nearest point in the orbit, that's the perihelion, and that's 1.47 times 10 to the 8th kilometers. And then the farthest distance, so I'm going to exaggerate a little bit and make the farthest distance much larger than it actually is in reality compared to the smallest. So the largest distance, the aphelion, is 1.52 times 10 to the 8th. And then the orbit looks something like this. Okay, so roughly an ellipse with the sun at one focus. So let's see, how are we going to find the semi-major axis and the eccentricity? Well, if you look at this diagram, from the perihelion, which I'll label P, to the aphelion, which is A, that's actually the long way across the ellipse. That's the major axis. So the major axis is 2 times little a, and that's the perihelion plus the aphelion. So 1.47 times 10 to the 8th kilometers plus aphelion is 1.52 times 10 to the 8th kilometers. Okay, so that means that the major axis is 2.99 times 10 to the 8th. And then to get the semi-major axis, we just divide that by 2. So 1.495 times 10 to the 8th. Okay, so there's the semi-major axis, and that's in kilometers. All right, so to find the eccentricity of the Earth's orbit, remember eccentricity is just the focal distance divided by the semi-major axis. Well, we know the semi-major axis, but we don't know the focal distance yet. Remember, the center in this orbit setup, the center of the ellipse is just kind of out in space somewhere. But what we can do is, we do know the semi-major axis already, and the semi-major axis is the distance from the center out to either one of the vertices. So we also know the aphelion, and that's from the sun out to the farthest point. That's that distance. So we can subtract those to find the distance from the center of the ellipse to the sun. And the distance from the center of the ellipse to the sun, well, the sun is at a focus, so the distance from the center to the sun is going to be the focal radius. So we can take our, so for C, we can take our aphelion, which is 1.52 times 10 to the 8th, and then subtract our semi-major axis, which is 1.495 times 10 to the 8th kilometers. Divide that by our aphelion, so 1.495 times 10 to the 8th, and then we'll have our eccentricity. So 1.52 minus 1.495 is 0.025 divided by 1.495, and that gives us 0.0167. So pretty small eccentricity. And remember, what that actually means is that the orbit of the Earth is actually pretty close to a circle. That's true of most of the inner planets. Their eccentricity of their orbits is pretty small. When you start getting to minor planets like Pluto's, then the eccentricities can get kind of big. All right. Let's also figure out where is the other focus. Remember, the other focus of the orbit of the Earth is just hanging out in space somewhere. Let's figure out how far is it from the sun. Well, we found the focal distance C, so the other focus right here is just 2 copies of C away from the sun. So the distance from the sun to the other focus is just 2 times C. So let's see, C was, I guess we didn't actually write it down, it's 0.025 times 10 to the 8th, and we need twice that. So that's going to be 0.05 times 10 to the 8th, which is 5 times 10 to the 6th kilometers.